research focuses on, oh, very good. Her research focuses on developing spatiotemporal models designed to analyze fish movement, and she's been using HPC to process large-scale spatial data and implement computationally intensive statistical models. And so basically what I will do is at 10 minutes, I will raise my hand on the Zoom, and then you would have to wrap up, and then at 15, I'll interrupt. So without further ado, Mashid, if you're ready, you want to share your screen?
Can you please post the, oh, thank you.
Can you see my screen?
Yes.
Okay. Hello, everyone. Thanks for joining us today. My name is Mashid Ahmedian. I'm, as Eric said, a PhD student at VCU. I'm an affiliated student at Virginia Institute of Marine Science and a graduate fellow at Virginia Sea Grant. And today I'm going to talk about my journey with HPC, why I need it in my research, and what challenges did I face when I wanted to use it. My research is at the intersection of data science and marine science, and it focuses on developing new methodologies to predict unseen locations of fish across the space and time. So I worked with two different data sets. One of them was sharks swimming in the Pacific Ocean, and another one was cobia, which is swim along the East Coast in Atlantic, and it's a very important recreational fish for the fisheries management of all the East Coast states. So let me start with an example to give you a picture about what exactly my research is. So imagine that you're watching a movie on an old scratched up CD. As you watch the movie, you may miss some of the frames. So you keep guessing what happened. So for example, you're watching this person leaving the house, and in the next scene, you get this fuzzy picture. And then after a few seconds, the picture comes back, but now it's a different picture. The person arrived at, for example, one of the university buildings and holding a coffee in hand. So you can still follow the story, but you keep guessing that what happened in between. So what you know is that person started at his house, then we don't have any information, it's the blank information, and then he arrived at university. So we want to have a guess that makes this movement logical. So let's see. We know where he started, we know where he ended, and we know that he has a coffee in hand. So maybe he stopped by at a coffee shop and get a coffee. So we had this blank blank scene of a movie, and we filled it in. Now imagine that you have thousands of different movies at the same time, thousands of different movies with thousands of different blanks, and you want to estimate, you want to guess what happens in each of that. Now let's go further. Instead of movies, we have a fish that is swimming in the sea. So you see the fish in an area in the ocean, and then the fish vanish. You don't know where it went. But like 4 hours later, you see it in another area swimming. And you're wondering, well, what path did this fish take to get to that area? This is what actually I do. I develop methodologies to predict this path, a step by step, constructing the fish movement through time and space. While we wanted to make it logical and realistic. So before move on, I wanna answer these questions that why do we have these sparse missing values in our data set? Why we have undetected locations? Because many people ask me this when I'm talking about it. So there are different technologies available for tracking animals, but in this case, we have two different types, satellites and acoustic receivers. And for the satellites, the tags are attached to the fish body, in this case, sharks. And whenever the shark is swimming on the surface of the water, the satellite could track it and detect the tag and record the location. In the other case, we have acoustic receivers, and they have this detection range that whenever the fish is swimming in that detection range, that tag inside the fish body makes the buzzer sound that gives signal to the acoustic receivers and makes it realize that the fish is swimming in that area. So the receiver considers that in that time, the fish was in that area. It's not actually the exact location of the fish. So in either of these cases, whenever the fish is beyond the detection area, if the fish is swimming under the surface of the water, or if it's swimming beyond the detection area of the receivers, we don't have any clue of where the fish was. So now let's move on to HPC. Why do I need HPC? The first reason is that each predicted step depends on the previous one. It's kind of a chain reaction. Each step is building on the previous step. Each estimates it's building based on the previous estimate. And this nested thing is, of course, time consuming. Another one is that we cannot accurately choose one certain path and say that this is the certain path that fish took. We have to run the algorithm thousands of times to simulate the most probable passes for the fish. Another thing is that there's a huge data set. This is not just one fish. It is not just one blank. One missing value. It's a lot of missing values because the fish was tracked over a large period of time. And this is just not one fish. This is a lot of fish with different movement paths. So it needs millions of calculations. Beyond all of that, from a statistical point of view, we're using a Bayesian inference. And this means sampling from probability distributions each time and updating the predictions. This also is time consuming. So with all that I said, running thousands of simulations per fish across many fish that we have means millions of calculations. And that's why, at the first place, I decided to use HPC facilities. So now let's move on to just some of the challenges that I personally faced. One of them was that I usually run everything on my computer, no matter what, and it took time. But when I started using HPC, I realized that even on HPC, large single jobs take time. So I had to use either parallel computing or divide my workload to multiple jobs and submit them. For that also, I had to learn bash scripting and automating the job with that. So I don't have to submit them manually myself. Another one was learning about the queue system. Many people are using the HPC facilities at the same time. And there are job schedulers that prioritize people's job. And for that, I had to learn a scheduler's comments. Besides that, what I personally preferred was to wait until midnight, that maybe many people are not using that HPCs, and just submit my job. Another thing was, which is actually for maybe just beginners, is that you don't get to debug your code at the same time that you're running it. It's not your personal computer. You have to run a small jobs on your personal computer, make sure that it doesn't have any errors, and then submit your job, because you don't see the jobs until after everything's done. But with all that I said, it's been a while that VCU has the graphical user interface, and many students are using that. It makes everything easier. There's no need to learn about schedulers command or I don't know, bash scripting. It's way easier. I know that at least at VCU, many students are these days using HPC because it's now easier to use. Of course, that some people maybe don't like it because it took away the feeling of exclusive club feeling from them, but it's good that many people are using it. Thank you for your time, and if you have any questions, I'm glad to answer.
Thank you, Marcia. Does anyone have any questions to start? We have a little bit of about 2 minutes of extra time. All right, clapping. Well, I can start. I would just be curious. Am I right to assume this is mostly all in Python?
No, it's on R,
Oh,
some parts recently on C++, yes.
R and C++. Well, that's interesting. Very nice. And did you mainly, you said that a skill that was interesting is you said to learn how to cut up large jobs into smaller runs. Is that something that, what was sort of the approach for that? Did you have lots of serial runs you could run simultaneously, or did you have the ability to actually parallelize parts of code?
There's two different types. So for like Bayesian estimations that I could use parallel running, which is just basically a command in R that I try to put it on different nodes so it runs faster. But for the multiple jobs, what I did for example, for sharks, we know that they move independently. So for each of them, I can run algorithms independently. So what I did that I put like different codes for them to run at the same time because I know that it's just not affecting each other, it's just independently.
And lastly, my last question is that you said there's millions of calculations. Do you know like roughly what the footprint of all your data is? Are we talking like lots of terabytes? I mean, just roughly. I'm just curious.
Oh, I don't have estimate on my mind.
All right, does anyone else have any questions? Okay, well, let's thank Rashid again. And I'll be clapping here too. Very good. All right, our next speaker will be James Giroux. While he's getting set up, I'll just tell you he is a PhD candidate working at the intersection of nuclear physics and data science at William & Mary, focused on primarily applications of generative AI, computer vision, and Bayesian deep learning for physics event reconstruction, and soon to be from our 51st state. I thought you might.
That's a good one. Okay, so everybody can hear or see my slides okay and hear me okay?
Yes.
Okay, perfect. Okay, so I guess first I want to say thank you to our first speaker for her wonderful presentation. Unfortunately for you guys, my slide quality is not as high as hers, so you'll have to bear with me through this. So this is sort of my real story, I guess, about using HPC. So about me, my name is James Giroux. I grew up in a small town in rural Canada, which may end up being the 51st state here. I guess we'll see. I did an undergrad degree in physics, which then I followed up with a master's in electrical and computer engineering at the University of Ottawa. And now I'm currently pursuing my PhD in data science here at William & Mary. So my workflows, so I guess if you'll allow me, this is sort of my 30-second blurb to try and convince you guys that I'm actually qualified to be giving you guys this information today. So I'll leave it up to you if you think that's true or not. But generally the things that I'm doing, at least nowadays, are things like fast simulation of Cherenkov detectors with generative AI, reconstruction of Cherenkov detectors with just general deep learning. So when I'm saying reconstruction, this is basically just something hit my detector and I want to know what it was. So very simple classification tasks. And then also we do some Bayesian deep learning. So for specific physics interactions such as deep inelastic scattering, we are after high precision measurements. So we want to basically augment our network outputs with uncertainty so we can have a better analysis in downstream tasks. So when I was making these slides, I was thinking about what are the ways that I use HPC, and it really comes down to three main things. So the first thing I'll be doing quite a lot is pre-processing physics data sets. So generally, these are very, very large, so on the order of terabytes, sometimes 10, 20 terabytes of data. And I'm processing these using hundreds of CPU cores. They're essentially as many CPU cores as I can get, such that I can process such a large amount of data in an efficient manner, something that doesn't take 3 months to process through in a sequential manner. I also might be running simulations, so the outputs of these again could be on the order of terabytes, and also using hundreds of CPU cores. And so these two sort of upstream tasks, I would call them, are really formulating for my final end goal, which is actually training deep learning models. So generally, these jobs are large memory overhead. I'm basically compressing terabytes of data into as small package as I can. And then these are usually single or multi-GPU jobs, depending on the architecture that I'm using and whether or not it can be distributed. So how did I learn HPC? So my story is probably a little more traumatic than people who are starting out nowadays. So I was very minimal guidance and I was thrown into the fire. So I started using HPC when it was sort of relatively new, I would say, at least to the university that I was currently at. And we didn't have personalized clusters at universities. So essentially what would happen is I was just thrown into things like Compute Canada, the Open Science Grid, and Jefferson Lab. So for those not familiar with Compute Canada or the Open Science Grid, essentially what the idea is you take a whole bunch of universities who have HPC systems and you basically chain them together through one central node. And you can basically submit jobs anywhere in the country. So whether you're in Canada or the US, and sometimes these actually overlap as well. And then Jefferson Lab, which is a national lab. So these things were quite intimidating. So definitely to say that I was scared to submit jobs is an understatement. I'm sure those who have just started out using HPC can sort of agree with this sentiment. And I really had two sort of doubts in my mind. So one was, what if I request too many resources? And at the time when I first started using HPC, I didn't even know what resources meant, right? So what's a CPU? What's a CPU core? How are those things different? How much memory do I need? And then also I started doing this when GPUs weren't extremely popular. So what is this GPU thing? And do I even need one of those? And then probably my biggest concern or my biggest worry was, well, what if I actually break something, right? So obviously, if I'm submitting something like Jefferson Lab, I do not want to be responsible for breaking something. So that was a very big worry I had. So the good news is that you aren't going to break anything. Most likely, I will be the first one to say that since I've been here at William & Mary, I have managed to break a few things. I didn't actually physically break anything, but I have taken down some nodes. And I'll talk about this in just a few seconds here. As for resource requesting and knowing what you need, there's no really tried or true formula for this. This is something that you just gain intuition for over time. And at the end of the day, over requesting is not the end of the world. So if you over request, a couple CPU cores, a little bit of memory, even a GPU, you're not going to really inhibit anybody else's workflow in a significant way. So don't be worried about this. You live and you learn, and you gain this knowledge over time. The nice thing is also that HPC clusters are becoming common to most universities. So I guess in the modern age of data science, every university almost has an HPC cluster here, or at least a lot of them do. And these are generally smaller scale than something like a national laboratory. And so you have more personal experience with the administrators. So we're lucky here at William & Mary, for example, we have people like Eric, who is super helpful, super kind. And when you do break something and go to his office and say, hey, Eric, I think I took down a node, he's more interested in knowing how you did it than actually being concerned that you did it in the first place. So these people that we're able to work with at our universities are really, really helpful and always very, very kind. Another nice thing is that you know approximately everybody on the cluster. It depends if you're a graduate student or what. But if you do end up taking something down or making a mistake, and it impacts somebody else's workflow, 99% of the time, a simple sorry will cut it, and everybody moves on, right? And so in general, these things are much easier to work with. So learning to use HPC. So how would I recommend that someone goes about this? So how I've sort of made this slide is I have 3 different boxes that are numbered here, and they're also color coded, which I've for some reason decided to go with like a traffic light color coding. So green is really good, go for it. Yellow is okay, maybe use this. And then red is, last resort kind of thing. So first, ChatGPT is an amazing resource that we have access to, and I highly recommend you use it, especially when you're trying to learn how to use HPC, how to write submission scripts, and what these things in these scripts mean. You can use the workflow manager, or you can go through and read the actual documentation of the workflow manager. But this is going to be, lots and lots of time wasted flipping through pages, looking for specific commands. And the reality is that ChatGPT has already done this, right? So it's trained on the internet, it's read through this for you, and you can ask it very, very specific questions, and it'll give you nice answers. Sort of in between this is universities actually have guides. So for example, here at William & Mary, the folks over at GeoLab, which is Dan Ranfola's group, made this super nice guide that takes you from, the basic jobs to very, very complex distributed jobs. So if you have access to things like this, I definitely recommend you use them as well. Again, so just an example here, ChatGPT can actually even help you write your script. So if you have no idea what you're doing, but you'd have an estimate of sort of the resources you need, you can actually ask it to write the script for you. And then if you have no idea what these commands in these scripts mean, you can actually ask it to basically break down the script it just wrote for you and explain this one by one. And so this is generally much more efficient than actually reading through the workflow manager, at least in my opinion, in my experience. So general tips and tricks. So the sort of the sad reality of it is that resource contention on HPC is actually a game. And so as you scale up to using, say, resources at national labs, for example, this game becomes even more important. So you need to know the rules of the game and use them to get your jobs running. So generally what this means is that you're always trying to optimize your wall time. Jobs with shorter wall times are going to be running first. So if you can structure your jobs in such a way to have minimal wall times, you're going to be more efficient in getting these jobs running. If possible, break jobs, large jobs into smaller sub-jobs. So if you have a huge data set to process, don't process it in one large sequential job, break it up and do it in a bunch of smaller jobs. And a really good way to do this is to actually fully automate these processes with something like Python, right? So you can actually have a Python script that will write these submission scripts for you and submit your jobs. And this is much more efficient than actually doing it by hand. Say you need to submit 1,000 jobs, Python can do this, almost instantly for you, as opposed to hitting, run and enter 1,000 times. Another key thing to do is create restore points for your jobs so that if somebody like me does take down a node, you're able to essentially restore your job from where it was and also test your job on small sample sizes. So in conclusion, if you didn't get if none of these tips or tricks are going to be useful for you, at least I hope I was able to communicate that learning HPC can be intimidating, but don't be intimidated, right? Mistakes are going to happen, and that's just part of the learning process. It's never the end of the world. Sort of the key takeaways here: test your jobs on small sample sizes, create restore points for your jobs, and do things that make your life easier. So try to automate your workflows as much as possible. And yeah, sorry, I just heard some background noise, but that's everything. So thank you guys. And if you have any questions, I'll be happy to answer them.
All right, well, thank you, James. Very nice. I will let somebody else go first, but I definitely have a question if no one else is ready. Oh, I can believe Alistair has a hand up.
Yeah, can you hear me?
Yes.
Okay, cool. I was just curious. You obviously invested some time writing a Python script to create job scripts.
Yeah.
Is there a reason why you had to do that, or I mean, Slurm has array tasks, for example, submissions to facilitate submitting large numbers of jobs that are basically scripted.
Right. Yeah. So when I was doing these jobs, essentially what they were was either running over individual files, which is obviously a good case for that. And in other cases, it was actually submitting simulation runs. So either or would work, but I just usually opt to go for Python as it's something that I'm more familiar with.
Okay. I don't know what Eric's feeling about that from an admin point of view, if he would encourage that or would prefer to encourage people to use the
I think that we see a mixture of both. And I would say, as long as you're not doing anything nefarious, like, having a Python job, wake up, look at the queue and say, okay, I'll submit 1,000 things now. And, things like that, gaming the system a little too harshly,
Yeah,
it's probably fine.
fair enough.
All right.
Thank you. Thanks for your presentation.
Thank you.
I was just curious. I saw that you had talked about ChatGPT. I'm just wondering if you're using any of these, I don't know if you talked to Dan recently, but the windsurf editor, he's been that looks very nice.
Yeah, I've heard Dan talk about that. I haven't used it personally, but I know he's very excited about it.
Yeah, so for those who don't know, it's just an editor. I mean, I'm sure there's other tools like this out here, and I might sound naive because maybe there's 100 of these, but just an editor in which you can say, like, here, like James has in his slide, write me X. And it puts it into an actual editable file for you, which you can then just keep refining, sort of like an editor attached to ChatGPT. But anyway, that's a thing. I would just be curious. Is this all Python? Everything you do, James?
No. So Python and C++.
Oh, okay, that's right. Very good. Yeah, you got a favorite story of breaking something? Somebody's asking.
Do I have a favorite story of breaking something?
Yeah.
Yeah, the first time I think it was Astral. So if you notice here, I have this, where is it? Be careful of large IO. So one of the nodes at William and Mary, it's Astral, which is there's a CPU node and then a GPU node. And so I submitted a whole bunch of jobs to the CPU node. And they basically all went and tried to read files from the file system at once, which I learned from Eric is a bad thing to do. And basically somehow managed to pull down the CPU node and also the GPU node. And I remember that was the first time it happened, and I was quite traumatized. I thought I was going to be in a lot of trouble, but Eric was very kind about it and was actually very interested to know what I did and why both nodes came down. So it's probably my favorite one, yeah.
I would just say, yes, it's technically, we want to know what happened more than, because these things should not happen. So we just want to see the way we can prevent it. That's the most important thing to us.
Right.
Okay, if there's if there aren't any other questions, I will put my clapping up there, and we will ask the next speaker, Carolina Naranjo Velasco.
Naranjo. Thank you.
So bad.
But yes, we can say Naranjo. That works as well.
All right, Carolina Naranjo Velasco.
Thank you.
All right, she's a PhD candidate in data science at UVA, and an MSDS 2022 graduate. She brings a unique perspective as a Latina attorney specializing in constitutional law. Her research focuses on developing automations using HPC and AI tools for parsing legal documents and training language models to analyze text. Beyond her technical contributions, she strengthens diversity and data science through conference leadership and mentorship of underrepresented STEM professionals. So please take it away.
Oh. Thank you so much, Eric, for this kind presentation. Hi, everyone.
Elena, you went in the presenter mode, so we can see your double screen.
Oh, thank you. Oh,
Yes, thank you.
okay. So let me reshare again.
I believe you might have to press present first and then share that screen so that we just get the slideshow.
Okay.
Or that works too, I think.
Yeah, that's working now.
Now it's better?
Yes.
Yep.
Okay, awesome. Thank you. Thank you for letting me know that. Okay, so today I'm going to talk about my journey from, working as a constitutional lawyer and now working from analyzing law to computing workloads on Ribana high performance computing system at UVA. So just to give you a brief overview about my talk, I'm going to provide an introduction, the motivation of my research, what I'm doing on HPC, and also how I have been navigating a HPC as a new user, right? So I want to give you my like a brief introduction who I was a couple of years ago, and I was working as a constitutional lawyer in my home country. I'm from Colombia, and one of the main motivations that I transitioned from data science to data science, it was because I really want the stakeholders, in this case that I was working with victims of the armed conflict in my home country. They could understand better the jargon of legal documents, and also in that way they can access to their rights. So if people understand better the legal jargon that lawyers would use, it might be easier to make accessible systems and also pursue social justice. With that idea, so this is why I started this journey as a lawyer, going to data scientist. Now, today, I am a PhD student in data science, working at the intersection of law and data science, and I'm going to show you how HPC is for everyone, regardless their starting point, right? So I have been so fortunate to be involved in these labs. I have been working with Professor Harbison from Data Science School and also Professor Jean Fongi from the Computer Science Department. And with that, the big question is how a lawyer ended up running the Slum files in a Linux cluster. And more importantly, how you can leverage HPC even when your starting point was at that moment or now, like working on core documents in Word documents, right? This is the difference. The language is different, the interface is different. So with that, I'm going to give you my motivation, why I'm here today, talking about my research and why my research matters and why we need HPC to do part of my research, right? So I would highlight 3 characteristics of legal documents. Legal documents, again, I want to emphasize, they use a legal jargon. So a table is a table in the United States and I don't know, let's say England. So the meaning or the word of table doesn't change, right? But if we are going to use a specific word, for example, in this case, like we can use marital and property has a specific meaning in the family law. So this is going to differ from general users. Another characteristic of the legal documents is there are rich in citations, right? They have a tons of information inside those documents. Let's say core opinions contains or involves presence and status. And those citations, if we don't link with the document, they are going to lose this kind of segmented meaning or context that we need to understand the nuances of law. And lastly, and most importantly, especially for this, the use of HPC, is there are highly structured documents. And what I mean with that, right? So if we want to convert, and the legal documents are lengthy documents. Those documents can be spanned like 300 pages. And can you imagine to transform those pages into tokens is going to increase the dimensionality in the latent space, or that kind of transformation, how computers is going to read the data. With this introduction about the motivation of my research, this is why I'm here today, working at as a data scientist, and also, getting my PhD in data science. I use the Rivanna HPC basically for fine-tune large language models. So basically, the idea to use fine-tune models is to take already like a pre-trained model. In this can be, open source models like Llama, Mistral, and make that model take like a part of that model and make more specialized. And with that specialized training, this is part of my research because I work on creating benchmarking data sets. This is part of my research. So in this case, for example, I am working on, my main research is focused on court document decisions. You might guess why, because I am a constitutional lawyer, and constitutional lawyers read a lot of Supreme Court decisions and, many other like federal decisions as well. So basically, I focus on court decisions based on due to my background. So in this case, I want to, for example, do like a test classification task. In order to do this classification task, for example, I use the technique supervised learning. So with that, I am going to create like a label data set. And what does mean? So I use a Rivanna or HPC to do pre-processing. So clean up the data, make those transformations that I already explained to you. Why is the problem with the high dimensionality of the documents, and create this label data set using several GPUs. Don't ask me the number because I don't remember the number, but I use those GPUs to make more faster the pre-processing, the manipulation of my data. And lastly, we are just get a data set, a data that are going to introduce in the model. So this is an example of the distribution of the data split of my data set. So we are talking about 14 billion tokens in the training set, and 1 billion for the development, and 3 million for the test set. In total, like roughly 20 billions of tokens. So this is why it's important to use these services for my research. So once I use the CPUs of the Rivanna, so I do the training. So I am working specifically with Llama models, especially because they are open source, they facilitate the reproducibility, and yeah. So with that, I want to provide you the main key lessons I have been learning so far. So first of all is GPU utilization. It's not the same to set up a GPU that is for a model for 7 billion versus a model that is 13 billion, right? So in this case, at UVA, so for example, we need to use for a model specific 13 billion models, we use the GPU A100, which is the most potent GPU that we have. So that is important, GPU utilization. Another thing I learned is scaling up experiments. And this is the key, is you don't know, and I like to use some analogies sometimes, how we can digest this, right? So you are not going to learn, for example, if you want to learn a second language, so you might start with some basic grammar, maybe, right? Or start to, make some simple sentences in order to go to complex sentences. And with that logic is kind of the same using this system. So we need to start with a small, setting up some, for example, setting up like a suit sample of those tokens, and play with the parameters, the batch size, the learning rate. Those is going to help me to get better, facilitate the training that I am doing with the models. Another issue that I have learned so far is, for example, how we can play with the time limit that, for example, we have at Rivana. So in Rivana, there is like a 72 limit time. So I learned how can I make scripts to resume the checkpoint from the previous training, that the GPU, that we can utilize GPUs from the previous from the data that was already training and continue with this training. And for that, I use Python scripts to do that, and everything is organized on like a code base that I have been working on. And the other lesson that I have from this experience is also, just implement troubleshooting strategies. And one of the amazing things that I found on my experience using Rivana HPC is the iJobs. So I wasn't familiar, right? So I would have like a Word document before, reading like a core decision. And now that document that was, for example, in like a white interface, now I am reading everything in black interface. And this is amazing. This is part of the process that you need to be willing to learn, right? So these kind of like a troubleshooting strategies also works in order to get the predictions by the models. So I guess I'm running out of time. So I want to emphasize how you can navigate HPC as a new user. So I would highlight mentorship and collaboration, right? So I have been working close to Rivana consultants. For example, I had been kind of have mentor from one of the consultants. He's Marcus Bobar. He's an amazing mentor. He tries to sometimes help me out with all of the workflow I already show you. So this is important. Have good mentors in this process. Second, I have been attending office hours frequently. So I would say I am a frequent user of office hours on Rivana. And also, it's important also sometimes take advantage of your lab teammates. They can explain to you sometimes the debugging as well. And this is part of the, the main takeaways, I would say. So learning resources. So I get, this is also important, reading forums on Hugging Face, Stack Overflow, GitHub. Also ChatGPT, I would say ChatGPT is a good tool sometimes. However, it's kind of what I'm doing with my research. So we can use these large language models, but again, there is still the human feedback that we need to do in order to get a better understanding. This is why, for me, ChatGPT is connected with a good mentorship. And again, I want to highlight the troubleshooting the strategies using iJobs that, for example, Rivana provides to users at UVA. With that, I'm going to, open to questions. So thank you so much.
Thank you, Carolina. I was just, before we get into it, I was just curious, these iJobs that you have mentioned before, that looks like this, do you just mean that you're running interactive jobs to debug various workflows? Is that what it is? Okay, very good.
Yeah. And that was an important, experience, because I wasn't used to do that, right? So for me, it was a completely war, just getting like a document, long documents I was supposed to read before, and now it's, lines of code. I also have to learn Bash language, but I wasn't familiar with that before. So yeah, this is part of I have been using on iJobs.
Thank you. So does anyone have another question? Thank yous. All right. Well, maybe we could.
May I ask?
Oh, yes, absolutely.
Sorry.
that Carson?
Yeah, I think you're muted, Karsten.
Yeah, I think he was getting feedback.
Yeah, try.
Okay, trying again. Can you hear me
All
now?
Yes.
Okay, thank you. Well, first of all, thank you, Carolina, for the presentation, for making time to join us here today. My question is, what do you think, how prevalent is it now in the legal field to use HPC in large language models, whether it's research or more in, kind of an applied angle?
Yeah, thank you for your question. Maybe I wasn't clear at the beginning of the motivation, but again, the characteristics of legal documents is that they are high dimensional. So we cannot process those documents. We cannot do like a pipeline that is scalable using just your laptop. We need CPUs, we need the GPUs if we want to train those models. So this is why it's so crucial to use this kind of systems, especially the characteristics of legal documents, which are high dimensional.
Thank you.
So 20 million tokens. Could you give us, those of us that don't know what that means as far as size, is that absolutely outrageous? Is that typical for the type of problem you're doing? Give us a
That actually,
context.
that number should be less. I mean, it's not the worst, because basically I just, I have a corpus like a 27K documents. I just use a suit sample of almost 200 documents. And I use the services of Ribana to transform those documents into tokens. Tokens are numeric representation of words. So basically, tokens means numbers that we are going to introduce in a big machine for training, prediction, and so on. So this is what I mean with tokens. But yes, it's common. It's common, and it might be more. Especially again, the high dimensionality that legal documents are meant to be, and also that there are lengthy documents, so they have a lot of information. Yeah, Karthik, go ahead.
Yes, I had a question more on the inference side. So can you comment on like how HPC would be useful or can be used for performing inference on an LLM? Like training, yes, you can use dedicated resources for a fixed period of time. But for inference, is it going to be opportunistic, or do you need any dedicated resources for performing inferences?
Sorry, could you repeat the question? I didn't get it. Sorry.
So you kind of told about the fine-tuning part, right?
Mm-hmm.
You use a couple of millions and I'm assuming that you would reserve your resources for like maybe a couple of tens of hours or so, and then you perform your training, so on and so forth. So in terms of inference, which is usually less time probably, but you would probably need like all of the resources. So how do you kind of see that happen?
Yeah, I got it. Thank
HPC?
you. Yeah, so it's important to, for example, do like a GPU job arrays in order to manage this kind of in order to manage how we can approach this.
Okay.
All right. I believe that is the end of the questions, unless anyone has anything else quick. If not, I wanted to thank the three speakers for coming here and giving us three very, very useful presentations. And two things, if you haven't signed the sign-in sheet yet, it's in the chat. The link to it is in the chat. And also, if you're interested in joining VA-WHPC as far as getting more people to participate with us planning these events and stuff like that, please check out the website. That's also in the chat. And yes, the sign-in sheet was just posted again, so it'd be great if you can fill it out before you leave the meeting. And again, thank you everyone for showing up, and thanks again to our three speakers.
And please stay tuned for our next event that is going to be in April. So just please visit our website, VA-WHPC.org. There you're going to see the events. And also for those that are new and are not part of our mailing list, if you want to participate, I think that when you register, you would ask that question if you were still if you wanted to be part of the mailing list. So you can also sign up so that you get the announcements of the events that we have. Also, you're going to get information about different job postings that are related to the research computing field and different student events. We're also planning, we do every year, we do a student lightning talk presentation. So we're always looking for students that are, whether about to finish or mid of their journey. And we invite them to have lightning talks. Carolina, I wanted to ask you, which year are you in your PhD?
Yes, I am third year PhD student.
Okay. Well, it's very nice to meet you.
Yeah, likewise.
Jennifer, anything else you want to share, or Eric?
What's that?
Anything else we want to share?
No, I think we're okay. Thank you for pulling up the end there for me with the announcements. I appreciate it. All right. Well, thank you very much, everyone. We'll see you at the next event in April.
Thank you.
Thank you.
Have a great day. Thank you.